What if I told you that right now, as you're watching this video, you're already flying through space at 1.3 million miles per hour? Not just moving with Earth's rotation or orbit around the sun. I'm talking about your actual motion through the universe itself. And here's the truly mind-bending part. Even at that incomprehensible speed, if we wanted to visit every single galaxy in our observable universe, stopping at each one for just 1 second, it would take us longer than the current age of the universe. Not years, not millennia. We're talking trillions upon trillions of years. But here's what will completely shatter your sense of cosmic scale. There are approximately 2 trillion galaxies in the observable universe. 2 trillion. That's not counting stars. That's entire galaxies, each containing hundreds of billions of stars. And we're going to fly through every single one of them today. In the next 3.5 hours, you and I are going to accomplish what would be physically impossible for any civilization, no matter how advanced. We're going to experience something that defies the laws of physics themselves. Now, before we begin this journey that will fundamentally change how you see yourself and your place in existence, I need you to do something. Hit that like button right now. Subscribe to this channel, and down in the comments, tell me what country you're watching from and what time it is where you are. Because what we're about to explore transcends every boundary humans have ever created. Whether you're watching from Tokyo at midnight, London at noon, or Sao Paulo at dawn, we're all about to become cosmic travelers together. This isn't just a video, it's a transformation of perspective that you'll carry with you for the rest of your life. The story we're about to tell begins 13.8 billion years ago, with a violent birth, and ends with a question that will haunt you long after this video ends. Are we flying through these galaxies? Or are they flying through us? Let's start our engines. Before we can fly through every galaxy in the observable universe, we need to understand something that most people get completely wrong. What exactly is a galaxy? And why does it matter that we're limited to the observable universe? Here's your first mind-blown moment. A galaxy isn't just a collection of stars floating in space. A galaxy is a gravitationally bound system containing stars, stellar remnants, interstellar gas, dust, dark matter, and sometimes things we can barely comprehend like supermassive black holes, millions of times more massive than our sun. Think of it like a city in space. Except this city is so large that light itself traveling at 186,282 miles per second takes hundreds of thousands of years just to cross from one side to the other. Our home galaxy, the Milky Way, contains between 200 and 400 billion stars. Let me put that in perspective for you. If you started counting stars in our galaxy right now, counting 1 star per second, without ever stopping to eat, sleep, or rest, it would take you over 12,000 years to count them all. And that's just one galaxy. We have 2 trillion of them to visit. But here's where it gets weird, and this is crucial for understanding our journey. When we talk about the observable universe, we're not talking about the entire universe. We're talking about the portion of the universe from which light has had time to reach us since the Big Bang. The observable universe is a sphere centered on Earth, with a radius of about 46.5 billion light-years in every direction. That number seems wrong, doesn't it? If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? This is where your intuition about space completely breaks down. The answer lies in something called cosmic expansion. Discovered by Edwin Hubble in 1929. Hubble was observing distant galaxies at the Mount Wilson Observatory in California when he noticed something extraordinary. The farther away a galaxy was, the faster it appeared to be moving away from us. But these galaxies weren't moving through space itself, was expanding, carrying the galaxies with it. Think of it like baking raisin bread. As the dough expands, the raisins move apart from each other. But they're not moving through the dough itself is expanding. The raisins are galaxies, and the dough is space-time itself. This means that objects we can see now have moved much farther away during the time their light was traveling to reach us. The object we see 13 billion light years away has actually moved much farther during those 13 billion years of cosmic expansion. This expansion creates something called the cosmological horizon, a boundary beyond which we cannot see, not because the light hasn't been emitted, but because the expansion of space has carried those regions away from us faster than light can travel through space to reach us. It's like trying to walk up a down escalator that's moving faster than you can walk. Beyond this horizon, there could be trillions upon trillions more galaxies, but we'll never see them. They exist in a part of the universe that is forever beyond our reach, beyond our observation, beyond our knowledge. So when we embark on our journey through every galaxy in the observable universe, we're actually exploring only a tiny fraction of what might exist. The universe you cannot see might be infinite. Let that sink in for a moment. Infinite galaxies, infinite stars, infinite possibilities. But let's focus on what we can observe. Our journey will take us through three fundamental types of galaxies, classified by Edwin Hubble himself in 1926. We have spiral galaxies, like our Milky Way, with their majestic pinwheel arms of stars, gas, and dust. We have elliptical galaxies, which look like enormous, glowing footballs or spheres, containing mostly older stars and very little gas for new star formation. And we have irregular galaxies, cosmic misfits that don't fit into either category, often looking chaotic and disrupted, usually because they've had violent encounters with other galaxies. Here's something that will completely change how you think about galaxies. They're not stable structures peacefully floating through space. Galaxies are in constant motion, constantly evolving, and they're violent. They collide with each other. They merge. They tear each other apart through tidal forces. They're cannibals, consuming smaller galaxies and ripping them to shreds. In fact, our Milky Way is currently in the process of devouring at least two smaller galaxies, the Sagittarius dwarf elliptical galaxy and the Canis major dwarf galaxy. Right now, as you watch this video, these smaller galaxies are being stretched and torn apart, their stars being absorbed into our galaxy like a cosmic meal. And here's the kicker that sets up everything we're about to explore. In about 4.5 billion years, our Milky Way is going to collide with our nearest large neighbor, the Andromeda Galaxy. This collision is inevitable, and it's already begun. In a sense, the two galaxies are approaching each other at about 250,000 miles per hour. When they merge, they'll create a new elliptical galaxy that astronomers have already nicknamed Milky. Anyone living on Earth during that collision, if Earth still exists, will see the Andromeda Galaxy grow larger in the night sky over millions of years, until it dominates the entire view, its billions of stars swirling and mixing with our own in a cosmic dance that will reshape both galaxies entirely. But we're not going to wait 4.5 billion years. We're going to visit Andromeda today, along with every other galaxy we can observe. So how are we going to do this? For our journey, we're going to need to break several laws of physics. We're going to travel faster than light, much faster. We're going to compress billions of years of cosmic time into a few hours. We're going to shrink the incomprehensible distances of space into something our minds can grasp. This is a thought experiment on a scale never attempted before, but it's grounded in real science, real observations, and real data collected by some of humanity's greatest minds and most powerful instruments. Let me tell you about those instruments for a moment, because they're the reason we know any of this is possible. In 1990, NASA launched the Hubble Space Telescope, a revolutionary observatory that has fundamentally transformed our understanding of the universe. One of Hubble's most famous observations was the Hubble Deep Field, taken in 1995. Astronomers pointed the telescope at a tiny, seemingly empty patch of sky, an area about the size of a grain of sand held at arm's length, and let it stare at that spot for 10 consecutive days. What they found was absolutely staggering. That tiny, empty patch of sky contained about 3,000 galaxies. Thousands of entire galaxies in a space that looked like nothing to the naked eye. Then in 2003 and 2004, they did it again with even longer exposures, creating the Hubble Ultra Deep Field. This time they found about 10,000 galaxies in that tiny patch of sky. And most of those galaxies were so distant that we were seeing them as they appeared more than 13 billion years ago, when the universe was still in its infancy. We were literally looking back in time. More recently, the James Webb Space Telescope, launched in 2021, has pushed our vision even deeper into space and time. With its infrared capabilities, Webb can see through the cosmic dust that blocks visible light, revealing galaxies that existed just a few 100 million years after the Big Bang. These galaxies challenge our theories about how quickly galaxies could form in the early universe. Some of them are surprisingly large and mature, suggesting that galaxy formation happened faster and more efficiently than we thought possible. All of this observational data, decades of work by thousands of astronomers, has given us an increasingly accurate census of galaxies in the observable universe. That 2 trillion number I mentioned earlier comes from a 2016 study by Christopher Kinselis and his team, who used deep space images and mathematical models to estimate how many galaxies exist across the entire observable universe, including those too faint and distant for us to currently see with our telescopes. 2 trillion galaxies, each one a cosmic metropolis, each one with its own story, its own history, its own collection of stellar inhabitants. And we're going to visit every single one. Here's what that means in practical terms. If we classified these galaxies by type, roughly 70% would be spiral galaxies, about 25% would be elliptical galaxies, and about 5% would be irregular galaxies. By size, the vast majority, perhaps 99%, are dwarf galaxies, containing only a few billion stars each. These cosmic runts are the most common type of galaxy in the universe, but they're so faint that we can only detect the ones relatively close to us. The large galaxies like our Milky Way and Andromeda are actually the exceptions, the giants in a universe full of dwarfs. But size doesn't tell the whole story. Some of the most fascinating galaxies are the strange ones, the cosmic oddities that challenge our understanding. There are galaxies with rings instead of spiral arms. There are galaxies that look like jellyfish, with long tentacles of stars and gas streaming behind them as they move through space. There are galaxies that appear to have no dark matter at all, which shouldn't be possible according to our current models. There are galaxies that are almost completely invisible, made mostly of dark matter, with just a handful of visible stars. And there are galaxies so active, so energetic, that they outshine everything else in their cosmic neighborhoods. These are the quasars, and active galactic nuclei, powered by supermassive black holes, consuming material at a rate of several suns per year. Now here's the revelation that connects everything I've just told you. When we look at distant galaxies, we're not just looking across space, we're looking back in time. The farther away a galaxy is, the longer its light has taken to reach us, which means we're seeing it as it was in the past. The most distant galaxies we can observe appear to us as they were over 13 billion years ago, when the universe was less than 1 billion years old. These ancient galaxies look nothing like the majestic spirals we see nearby. They're smaller, more chaotic, more irregular. They're still in the process of forming, still accumulating the gas and stars that will eventually create the large, organized structures we're familiar with. This means our journey through every galaxy in the observable universe is also a journey through time. We'll be flying through the modern universe of today, but also the ancient universe of 13 billion years ago, and every epoch in between. We'll witness the evolution of cosmic structure itself, watching as small, irregular proto-galaxies merge and grow into the grand spirals and massive ellipticals that dominate the modern cosmos. Are you ready? Because we're about to leave Earth, leave our solar system, leave our galaxy, and embark on a voyage that will show you the universe as no human has ever seen it. We're going to experience 2 trillion cosmic destinations, each one unique, each one containing mysteries we're only beginning to understand. But before we launch, I want you to understand something profound. This journey we're about to take, impossible as it is, represents something deeply human. We're a species that has existed for only about 300,000 years on a planet. That's 4.5 billion years old, in a universe that's 13.8 billion years old. We've only had telescopes for about 400 years. We've only understood that other galaxies exist for about 100 years. And yet, here we are, attempting to comprehend the entirety of observable creation, to mentally visit every galaxy in existence, to understand our place in something so vast that our minds can barely contain the concept. That's not just curiosity, that's courage. That's ambition. That's the human spirit reaching beyond its limitations to grasp something infinite. So buckle up. Our first stop is the nearest galaxy to the Milky Way, and what we find there is going to set the stage for everything that follows. Engines to full power. Launching in 3, 2, 1. We're accelerating now, leaving Earth behind at speeds that make light itself seem slow. As our home planet shrinks to a point of light, then disappears entirely, we pass through the outer edges of our solar system. There goes Neptune, the ice giant marking the edge of the planetary neighborhood. There goes the Kuiper Belt, home to billions of icy objects, including Pluto. And now we're entering the Oort cloud, a vast spherical shell of comets that extends nearly halfway to the nearest star. But we're not stopping at any stars. We're leaving our entire galaxy behind. As we pull back, the Milky Way reveals its true shape. We live in one of the spiral arms, specifically the Orion arm, also called the Orion Spur, about 27,000 light years from the galactic center. From here, looking at our galaxy from the outside, it's breathtaking. The spiral arms glow with blue young stars and pink nebulae where new stars are forming. The central bulge glows yellow-orange with older stars, and at the very center, invisible to our eyes but detectable through its gravitational influence, lurks Sagittarius A*, a supermassive black hole with a mass of about 4.1 million suns. The Milky Way is about 105,000 light-years in diameter, making it a large spiral galaxy, though not the largest by far. It rotates like a massive pinwheel, taking our solar system about 225 million years to complete one orbit around the galactic center. The last time we were in this position in our galactic orbit, dinosaurs were just beginning to dominate Earth. But we're not here to admire our home. We're on a mission. Our first destination is the Sagittarius Dwarf Elliptical Galaxy, one of the galaxies currently being cannibalized by the Milky Way. This galaxy is only about 70,000 light-years from Earth, making it one of our closest neighbors, though it's hidden behind the Milky Way's central bulge when we look at it from Earth. Here's what makes this galaxy fascinating. It's being torn apart by tidal forces from the Milky Way. Long streams of stars are being pulled from the dwarf galaxy, creating ribbons of stars that wrap around our galaxy like tinsel on a Christmas tree. The Sagittarius dwarf is orbiting through the Milky Way's disk, and every time it passes through, more of its stars are stripped away. In 1 billion years or so, this galaxy will cease to exist as a distinct structure. Its stars will be fully integrated into the Milky Way, becoming indistinguishable from our galaxy's native stars. This is galaxy cannibalism in action, and it's completely normal. Large galaxies, like the Milky Way, grow by consuming smaller galaxies. In fact, astronomers now believe that much of the Milky Way's stellar halo, the spherical cloud of stars surrounding our galaxy's disk, consists of stars stolen from smaller galaxies over billions of years. Our galaxy is built from the corpses of hundreds of smaller galaxies that came before. But let's accelerate now. We're heading toward our next target, the Large Magellanic Cloud, one of the most prominent features in the southern sky, though completely invisible to anyone living north of the equator. It's about 163,000 light-years from Earth. Here we are. The Large Magellanic Cloud, or LMC, is a satellite galaxy of the Milky Way, meaning it's gravitationally bound to us and orbits our galaxy. It's classified as an irregular galaxy because it doesn't have the clean spiral structure or smooth, elliptical shape of larger galaxies, but it does have a bar-like structure through its center and one spiral arm, suggesting it might have been a spiral galaxy before gravitational interactions with the Milky Way disrupted its structure. The LMC contains about 30 billion stars modest by galaxy standards, but it's one of the most active star-forming regions near us. This galaxy is basically a stellar nursery, with massive clouds of gas and dust continuously forming new stars. One of the most spectacular regions in the LMC is the Tarantula Nebula, a massive star-forming region that, if it were as close to us as the Orion Nebula, would cast shadows on Earth at night. It's one of the most intense star-forming regions known in our local universe. But the LMC is also historically significant. In 1987, astronomers observed a supernova in the LMC designated SN 1987, which was the closest observed supernova since the invention of the telescope. This supernova was from a massive star that exploded, and we were able to study it in unprecedented detail. We detected neutrinos from the explosion, confirming theoretical predictions about supernova mechanisms. We watched as the expanding debris crashed into material the star had ejected earlier in its life, creating glowing rings that we can still observe today with the Hubble Space Telescope. SN 1987A taught us that when we fly through galaxies, we're not flying through static museums. We're flying through dynamic, evolving systems where stars are being born, living out their lives, and dying in spectacular explosions all the time. The galaxy you visit today will not be the same galaxy a billion years from now. Next stop, the Small Magellanic Cloud, the LMC's smaller companion, located about 200,000 light-years away. This dwarf irregular galaxy contains only about 7 billion stars, but it's notable for having a lower concentration of heavy elements compared to the Milky Way. In astronomy, anything heavier than helium is called a metal, and the Small Magellanic Cloud is what we call metal poor. This tells us that it hasn't experienced as much stellar processing as larger galaxies. The first generation of stars in the universe contained only hydrogen and helium, the elements created in the Big Bang. All heavier elements were forged inside stars and spread through space when those stars exploded. The more generations of stars a galaxy has gone through, the more heavy elements it contains. The Small Magellanic Cloud's low metal content suggests it hasn't processed as much of its gas through stellar cycles as other galaxies. Now we accelerate further, heading toward the next significant structure, the Andromeda Galaxy, also known as M31. This is the moment many of you have been waiting for, our visit to the largest and most prominent galaxy in our local neighborhood. At 2.5 million light-years from Earth, Andromeda is actually the most distant object visible to the naked eye. On a clear, dark night, away from city lights, you can see it as a faint smudge in the constellation Andromeda. What you're seeing is light that left that galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools, long before the first humans. As we approach Andromeda, its magnificence becomes clear. This galaxy is bigger than the Milky Way, about 220,000 light-years in diameter, containing approximately 1 trillion stars. That's 2 to 3 times as many stars as our galaxy. It's a massive spiral galaxy with a prominent central bulge and multiple spiral arms. Through telescopes, it's one of the most photographed objects in the night sky, a cosmic masterpiece of swirling stars and dust lanes. But here's what makes Andromeda truly special. Unlike most galaxies, which are moving away from us due to cosmic expansion, Andromeda is moving toward us at about 250,000 miles per hour. As I mentioned earlier, In about 4.5 billion years, Andromeda and the Milky Way will collide and merge. Computer simulations of this collision show that it will be spectacular. The two galaxies will pass through each other, then fall back together, and finally merge into a single giant elliptical galaxy over a process that will take about 1 billion years. Despite the violence of the collision, it's unlikely that any individual stars will actually collide. Space is so vast, and stars are so small relative to the distances between them, that a galaxy collision is more like two clouds of smoke passing through each other than two solid objects crashing together. However, the gravitational forces during the merger will throw stars and solar systems into new orbits, completely restructuring both galaxies. Our Sun might end up in a completely different part of the merged galaxy, or even be ejected into intergalactic space. Let me tell you something mind-blowing about observing Andromeda. When astronomers first realized that Andromeda was a galaxy beyond our own, it revolutionized our understanding of the universe's scale. For most of human history, we thought the Milky Way was the entire universe. There were debates about whether the fuzzy spiral nebulae that telescopes could detect were small objects within our galaxy or distant island universes beyond it. The question was definitively answered in 1924 by Edwin Hubble. Yes, the same Hubble I mentioned earlier. Using what was then the world's largest telescope at Mount Wilson Observatory, Hubble identified Cepheid variable stars in Andromeda. These are special stars whose brightness pulses in a regular pattern, and there's a relationship between their pulsation period and their actual luminosity. By measuring how bright they appeared versus how bright they actually were, Hubble could calculate their distance. His measurements showed that Andromeda was about 900,000 light-years away far beyond the boundaries of the Milky Way. Modern measurements have refined this to 2.5 million light-years, but Hubble's conclusion was correct. Andromeda was a separate galaxy. This single discovery expanded the known universe by a factor of millions. Suddenly, the universe wasn't just our galaxy. It was a cosmos full of countless galaxies, each containing billions of stars. It's hard to overstate how profound this realization was. It would be like thinking your house was the entire world, then discovering that billions of houses exist, spread across a planet larger than you could imagine. But we can't linger at Andromeda. We have 2 trillion galaxies to visit, and we've only seen a handful. Let's accelerate dramatically now, leaving our local group of galaxies, the collection of about 80 galaxies, including the Milky Way, Andromeda, the Magellanic Clouds, and dozens of smaller dwarf galaxies behind us. We're now entering the realm of the Virgo supercluster, a massive concentration of galaxies that contains our local group and thousands of other galaxies. The center of this supercluster is dominated by the Virgo cluster, located about 65 million light-years from Earth. As we approach the Virgo cluster, the number of galaxies explodes. There are over 1,500 galaxies in this cluster, ranging from massive ellipticals to small dwarfs. The cluster is dominated by 3 giant elliptical galaxies, M87, M86, and M84. Let's visit M87 first, because it contains one of the most famous objects in modern astronomy. M87, also known as Virgo A, is a supergiant elliptical galaxy containing about 1 trillion stars. At its center is an absolute monster, a supermassive black hole with a mass of about 6.5 billion suns. This is the black hole that was photographed by the Event Horizon Telescope collaboration in 2019, creating the first ever direct image of a black hole's event horizon. That image, showing a bright ring of light surrounding a dark circular shadow, was a triumph of human ingenuity, requiring a network of radio telescopes spread across the entire planet, working together as a single Earth-sized telescope. What makes M87's black hole so special is that it's incredibly active. It's consuming massive amounts of material, and in the process, it's launching a jet of particles and radiation into space at nearly the speed of light. This jet extends for about 5,000 light-years, making it one of the most dramatic features we can observe in any galaxy. The energy being pumped into this jet is staggering, equivalent to countless supernovae exploding continuously. Here's your next mind-blown moment. The black hole at the center of M87 has an event horizon, a point of no return, that's about 24 billion miles across. That's about 4 times the size of our solar system. This single black hole is larger than the orbit of Pluto. And it's not a solid object. It's a region of space-time so warped that not even light can escape its gravity. Think about that. A region of pure gravitational distortion, large enough to swallow our entire solar system and not even notice. Flying through M87, we'd see billions of stars in chaotic orbits, not the organized spiral patterns we're used to from the Milky Way. Elliptical galaxies formed through galaxy mergers, and they've used up most of their gas in star formation, leaving behind predominantly older red stars. These are the retirement homes of the galaxy universe places, where the most intense star-forming activity is long over, and the remaining stars are slowly aging. We're accelerating now, flying through cluster after cluster. There's the Fornax cluster, about 62 million light-years away, containing about 58 major galaxies. There's the Centaurus cluster, roughly 170 million light-years distant. Each cluster contains hundreds or thousands of galaxies, and the clusters themselves are arranged in even larger structures called superclusters. But here's where our understanding of cosmic structure gets truly weird. Superclusters aren't the largest structures in the universe. Recent observations have revealed that superclusters are arranged into massive filaments, walls and sheets of galaxies separated by vast voids where almost no galaxies exist. These structures are so large that they stretch for hundreds of millions of light years. Picture the universe as a cosmic foam or sponge. The galaxies and clusters are concentrated in thin walls and filaments surrounding enormous empty bubbles. The largest known structure, the Hercules Corona Borealis Great Wall, is a galactic filament about 10 billion light-years long. Light itself, traveling at its maximum possible speed, would take 10 billion years to cross this structure. It's so large that it challenges our theoretical understanding of how such structures could have formed in the age of the universe. We're flying through these structures now, passing through millions of galaxies in what feels like seconds. Each galaxy we pass contains billions of stars, and each star might have planets, and some of those planets might have conditions suitable for life. The numbers become so staggering that our minds struggle to process them. If even 1 in a million stars has a planet with life, and even 1 in a million of those has intelligent life, there could be trillions of civilizations in the universe. And we're flying past their homes right now, completely unaware of them, as they're completely unaware of us. Here's something that should give you chills. Some of the galaxies we're passing right now contain astronomers who might be looking back at our galaxy. The Milky Way, seeing it as it was millions or billions of years ago, wondering if anyone is out there looking back at them. And we are. We're flying through their home right now. But we need to address something important. At this pace, flying through millions of galaxies, you might start to think they all blend together, that one galaxy is much like another. That would be a mistake. Every galaxy is unique, shaped by its specific history of formation, mergers, and evolution. Some galaxies are still actively forming stars at tremendous rates. These are called starburst galaxies, and they're creating new stars hundreds of times faster than the Milky Way. Some galaxies have been stripped of their gas by interactions with other galaxies, or with the hot intergalactic medium in galaxy clusters, turning off their star formation entirely. Some galaxies are in the midst of violent mergers, their structures distorted into bizarre shapes. And some galaxies are so old and undisturbed that they've maintained their structure for billions of years. One galaxy I want to highlight is NGC 4038 and NGC 4039, collectively known as the Antennae galaxies. These are 2 spiral galaxies, located about 45 million light-years away in the constellation Corvus, and they're in the process of colliding and merging. The collision has been ongoing for a few 100 million years, and it won't be complete for perhaps another few 100 million years. But what makes them spectacular is that the gravitational interaction has pulled out long tails of stars and gas from both galaxies, creating two long antennae that give the pair its name. These tails stretch for hundreds of thousands of light years, and they're studded with bright blue regions where intense star formation is occurring. The collision has compressed gas clouds, triggering an enormous burst of star formation. Thousands of new star clusters are being born in this cosmic collision. Flying through the antennae galaxies would be like flying through a stellar fireworks display. Everywhere you look, new stars would be blazing to life in brilliant blue-white clusters, while the distorted structures of the parent galaxies swirl around you in chaotic spirals. Now we accelerate even more, our velocity increasing exponentially. We're flying through millions of galaxies per second now, and we need to because we have so far to go. We're leaving the nearby universe behind and pushing deeper into cosmic history. Remember, as we fly farther from Earth, we're also flying back in time. The light from distant galaxies takes longer to reach us, so we see them as they were in the past. At about 200 million light years from Earth, we're seeing galaxies as they were 200 million years ago, during the Jurassic period on Earth, when dinosaurs walked the planet. At 500 million light years, we're seeing galaxies as they were during the Cambrian explosion, when complex life was just diversifying in Earth's oceans. At 1 billion light years, we're seeing galaxies as they were before the first animals crawled onto land. We push deeper. 2 billion light years. 5 billion light years. At this distance, we're seeing galaxies as they were before our solar system even existed. The Sun formed 4.6 billion years ago, so any galaxy more than 5 billion light years away is being seen as it was before our home star was even born. At 10 billion light years, we're seeing galaxies as they were just a few billion years after the Big Bang. These galaxies look different from modern galaxies. They're smaller, more irregular, more actively forming stars. The universe at this epoch was a more violent, energetic place. Galaxy mergers were more common. Quasars, those incredibly bright active galactic nuclei, powered by supermassive black holes, were more prevalent. The night sky of any planet in this era would have been dramatically different from ours, filled with bright, active galaxies blazing with the light of billions of young, hot stars. We're at 12 billion light years now, seeing galaxies as they were when the universe was less than 2 billion years old. The first galaxies formed only a few 100 million years after the Big Bang, so we're seeing some of the earliest galactic structures. These ancient galaxies are much smaller than modern galaxies. Many would qualify as dwarf galaxies by today's standards. But they're important because they're the building blocks. Through countless mergers over billions of years, these small galaxies combine to create the massive galaxies we see in the modern universe, including the Milky Way. Here's a profound realization. Every atom in your body was forged in stars and galaxies like these. The hydrogen in your body was created in the Big Bang, but the carbon, nitrogen, oxygen, and every other element heavier than helium was created inside stars, then released into space when those stars exploded as supernova. Those elements eventually became part of new stars, new planets, and eventually you. You are literally made of galaxy stuff. Your body contains atoms that have been through multiple generations of stars, that have existed in multiple galaxies, that have traveled across billions of light years of space before becoming part of you. When we fly through these ancient galaxies, we're flying through places that might have contributed the very atoms that now compose your eyes, your brain, your heart. At 13 billion light years, we're approaching the edge of what we can currently observe. The galaxies here are extremely faint and difficult to detect, but they're crucial for understanding the early universe. The James Webb Space Telescope has recently detected galaxies at these distances that are surprisingly large and mature, challenging our theories about how quickly galaxies could form after the Big Bang. One galaxy recently discovered by Webb, JADES G1320, is seen as it was just 330 million years after the Big Bang. This galaxy shouldn't exist according to our previous models. It's too large, too structured, too mature for its age. It's forcing astronomers to reconsider how rapidly the first galaxies formed and grew. This is one of the most exciting aspects of exploring the early universe. We keep finding surprises that challenge our understanding and force us to refine our theories. And now we're at the edge, about 13.4 billion light years from Earth, seeing galaxies as they were just 400 million years after the Big Bang. This is as far as we can currently see with our most powerful telescopes. Beyond this distance, galaxies become too faint and too red-shifted for even our best instruments to detect them clearly, though we know they're there. But our journey isn't over. We've been flying radially outward from Earth. But remember, the observable universe is a sphere surrounding us in all directions. We've only explored one path through this cosmic sphere. To visit every galaxy, we need to systematically cover the entire volume of the observable universe. So now we begin a systematic sweep, flying through layer after layer of cosmic structure, covering every direction from Earth, visiting every galaxy cluster, every filament, every wall, and every void. This is where the numbers become truly astronomical. We're passing through millions of galaxies per second, then billions per second, then trillions per second, as we accelerate to incomprehensible speeds. If you're feeling overwhelmed by the scale, you're not alone. This is a normal human reaction to cosmic immensity. Our brains evolved to understand the African savanna, not the observable universe. We're built to comprehend distances of kilometers, not billions of light years. We're built to understand timescales of years, not eons. When we push our cognition to these scales, it's like trying to run software on hardware that wasn't designed for it. It glitches. It struggles. It feels impossible. But here's the beautiful part. We can do it anyway. Through mathematics, through science, through imagination, we can transcend our cognitive limitations and grasp something far larger than ourselves. That ability is uniquely human and profoundly powerful. Let me give you a retention hook before we continue. In the next section, we're going to explore what happens when we reach maximum speed, when we're flying through every remaining galaxy in fractions of a second. And we're going to encounter something that will completely change how you think about the universe itself. Something that suggests the universe might not be what we think it is at all. But right now, pause for a moment. Look at your hands. Those atoms were forged in stars and galaxies we're flying through right now. You're not separate from this cosmic journey. You're a part of it. Every breath you take connects you to the entire universe across all of time. Let that sink in, and then join me as we accelerate to our maximum velocity and discover what awaits us at the true edge of existence. We're at maximum velocity now, flying through the remaining galaxies at a pace that defies description. Billions of galaxies per second. Trillions per second. The entire observable universe is flowing past us in a stream of light and matter. At this speed, individual galaxies blur together into vast structures. The filaments and walls I mentioned earlier become visible as coherent features, like highways of light stretching across the cosmos. And now something strange happens. As we systematically visit every galaxy in every direction, covering every part of the observable universe's volume, we begin to notice something peculiar. The universe looks roughly the same in all directions. This might not sound surprising, but it should be. Let me explain why this is actually mind-blowing. The observable universe has a radius of about 46.5 billion light years. That means we can see objects in opposite directions that are separated by about 93 billion light years. But the universe is only 13.8 billion years old. Even if two regions at opposite ends of our observable universe had been exchanging light signals at the speed of light since the moment of the Big Bang, they would not have had enough time to influence each other. They should be completely independent, with no way to coordinate their properties. And yet, when we look at the universe in all directions, the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang, is the same to within 1 part in 100,000. The distribution of galaxies is similar in all directions. The large-scale structure of the universe looks similar no matter which way we look. How is this possible? How can regions of space that have never been in contact with each other be so similar? The answer is something called cosmic inflation, proposed by physicist Alan Guth in 1980. The theory suggests that in the first fraction of a second after the Big Bang, specifically from about y-36 seconds to 10 to 32 seconds after time, began, the universe expanded exponentially, growing by a factor of at least 1026 in an incomprehensibly brief moment. During this inflationary period, a tiny region of space that was in causal contact, small enough that all parts of it could exchange information, expanded to become larger than our current observable universe. This means that all the galaxies we're flying through, spread across 93 billion light-years of space, were once contained in a region smaller than an atom. They were in contact with each other, able to reach thermal equilibrium, before inflation stretched them across the cosmos. That's why the universe looks uniform in all directions. It all came from the same tiny, homogeneous patch of spacetime. Think of it like this. Imagine drawing a pattern on a deflated balloon, and inflating the balloon to an enormous size. The pattern would be stretched across the balloon's surface, but it would still be recognizable as parts of the same original pattern. That's what inflation did to the universe. It took a tiny, uniform region and stretched it to cosmic scales. But here's where it gets really weird, and this is your next major mind-blown moment. Inflation might not have stopped everywhere at the same time. While inflation ended in our part of the universe, allowing the Big Bang to proceed normally and galaxies to form, inflation might still be continuing in other regions beyond our observable universe. In fact, according to a theory called eternal inflation, developed by Alexander Valenkin and others in the 1980s, inflation creates an infinite number of separate bubble universes, each with potentially different properties, different physical laws, different values for fundamental constants. If eternal inflation is correct, then our observable universe, with all its 2 trillion galaxies, is just one tiny bubble in an infinite cosmic foam of universes. The universe beyond what we can observe might be infinite and infinitely varied. There might be regions where the force of gravity is stronger or weaker, where electrons have different masses, where atoms can't form at all, or where entirely different physical phenomena occur. This is called the multiverse hypothesis, and it's deeply controversial in physics. Some scientists embrace it as a natural consequence of our best theories. Others reject it as untestable metaphysics rather than real science. But regardless of whether it's true, the fact that our best scientific theories lead us to seriously consider such possibilities should tell you something profound. Reality is far stranger than our everyday experience suggests. As we complete our systematic sweep through every galaxy in the observable universe, visiting each one in our impossible journey, we're not just exploring our universe, we're touching the limits of what can be known. Beyond the cosmic horizon, there might be infinitely more galaxies, infinitely more universes, infinitely more possibilities, but we can never observe them. They're forever beyond the reach of our telescopes, beyond the reach of light itself. Let me tell you about another scientist whose work is crucial here. Roger Penrose, who won the Nobel Prize in Physics in 2020 for his work on black holes and cosmology. Penrose has proposed something called conformal cyclic cosmology, a mind-bending idea that our universe might be just one eon in an infinite cycle of universes. According to Penrose, the universe will eventually expand forever, with all matter decaying into radiation. But in the infinite future, when only radiation remains and all sense of scale is lost, the universe might forget how big it is. At that point, the end of our universe becomes mathematically identical to the beginning of a new Big Bang, and a new universe begins. If Penrose is right, our universe had a predecessor, and it will have a successor. The galaxies we're flying through right now might have analogs in previous universes and future universes, eternally recurring in an infinite cycle of cosmic death and rebirth. These ideas push us to the absolute edge of human knowledge. We've gone from flying through nearby galaxies like Andromeda to contemplating whether our entire observable universe is just one bubble in an infinite multiverse, or one eon in an eternal cycle of cosmic rebirth. This is the natural consequence of asking what's next. At each stage of our journey, we started with our local neighborhood and pushed outward until we reached the ultimate boundaries of what can be known. But let's bring this back to something tangible. We've now visited every galaxy in the observable universe, all 2 trillion of them. We've seen dwarf galaxies and giant ellipticals. We've witnessed spiral galaxies like our own and irregular galaxies distorted by collisions. We've flown through ancient galaxies, forming when the universe was young, and modern galaxies in our cosmic neighborhood. We've covered a volume of space containing more than Y stars. That's 1 septillion stars. And here's the most profound thing. In all of that space, among all of those stars, in all of those galaxies, we don't yet know if we're alone. We haven't found definitive evidence of life anywhere except Earth. This is sometimes called the Fermi paradox, after physicist Enrico Fermi, who asked, if intelligent life is common in the universe, where is everybody? Why haven't we detected alien civilizations? There are many possible answers. Maybe life is common, but intelligent life is rare. Maybe intelligent life tends to destroy itself before it can expand into the galaxy. Maybe civilizations are out there, but haven't tried to contact us, or their signals haven't reached us yet. Maybe we're looking in the wrong way, at the wrong wavelengths, for the wrong kinds of signals. Or maybe, and this is the lonely possibility, we're the first. Perhaps in all of those 2 trillion galaxies, across all of those septillion stars, Earth is the only place where the universe has become aware of itself. If that's true, then our journey through every galaxy takes on even greater significance. We're not just tourists observing the cosmos, we're the universe exploring itself. Every time you look up at the night sky, you're a piece of the universe that has become conscious, examining the whole that it's part of. That's not just poetic, that's literally true. The atoms in your brain that allow you to think and wonder about the cosmos were created in stars in galaxies far away. You are the universe, arranged in such a way that it can ask questions about itself. Carl Sagan, the famous astronomer and science communicator, said it beautifully. We are a way for the cosmos to know itself. Every human who has ever looked up at the stars and wondered is participating in this cosmic self-awareness. But we're not done yet. Our journey through space has taken us to the edges of the observable universe, but we need to explore something even stranger. What happens when we consider time differently? What if we could visit not just where galaxies are, but when they are? What if we could see the same galaxies at different points in their histories? That's what we're going to explore next, the time dimension of our cosmic journey. We're going to revisit galaxies we've already seen, but we're going to see them at different epochs, watching them evolve and transform across billions of years. We're going to watch galaxies being born, growing, colliding, and eventually dying. We're going to witness the entire life cycle of cosmic structure. Here's your next retention hook. In the next section, we're going to focus on one specific galaxy, one we've already visited, and watch its entire history from beginning to end. And what we discover about this galaxy's fate will reveal something unsettling about the future of the entire universe, including our own galaxy and every galaxy we visited. But before we move on, take a moment to appreciate what we've done. We've accomplished the impossible. We visited every galaxy in the observable universe. We've flown through structures spanning billions of light years. We've touched the edge of what can be known. And most importantly, we've done it together, you and I, separated by space and time in the real world, but united in this journey of imagination and discovery. That connection between you and me, between humans and the cosmos, between the conscious universe and itself, is what makes this journey meaningful. We're not isolated beings on a small planet. We're part of something incomprehensibly vast, and through science and imagination, we can touch all of it. Now, let's explore time. To understand what we're about to do, imagine you have a time-lapse video of a tree. You could watch it grow from a seed, develop into a sapling, mature into a mighty oak, and eventually decay and return to the soil. Each frame of the video shows the tree at a specific moment, but the video as a whole shows you the tree's entire life story. We're going to do something similar with galaxies, but there's a twist. We don't need a time machine. We already have the equivalent of that time-lapse video because of how light works. Remember, when we look at distant galaxies, we're seeing them as they were in the past. The farther away a galaxy is, the farther back in time we're seeing it. This means that by observing galaxies at different distances, we're essentially seeing different stages of galactic evolution. A galaxy 2 billion light-years away is seen as it was 2 billion years ago. A similar galaxy 8 billion light-years away is seen as it was 8 billion years ago. By comparing these galaxies, we can reconstruct how galaxies evolve over time. Let's focus on spiral galaxies similar to the Milky Way and watch their evolution across cosmic time. At 12 billion light-years away, we see protogalaxies, small, irregular collections of gas and young stars. These are the ancestors of modern spiral galaxies. They're chaotic, actively forming stars at enormous rates, and frequently merging with other protogalaxies. The universe at this epoch is crowded, with galaxies much closer together than they are today. The merger rate is high, and most galaxies are growing through accretion of smaller galaxies and gas clouds. One thing you'd notice if you were actually present in this era: the night sky would be dramatically brighter. The cosmic microwave background would be warmer, glowing with visible light instead of being invisible microwaves as it is today. The expansion of the universe has stretched and cooled this radiation over billions of years. But in the early universe, it was hot enough to see. Plus, the higher density of stars and galaxies would make the night sky more crowded with light. At 10 billion light-years, 3.8 billion years after the Big Bang, we see these protogalaxies beginning to organize into more structured forms. Some are developing disk-like structures as they rotate. The gas is settling into flattened distributions, and stars are beginning to form in organized patterns. These are the teenage years of galaxy formation, awkward, transitional, not yet mature. At 8 billion light-years, 5.8 billion years after, the Big Bang spiral structure is becoming clear in many galaxies. The characteristic pinwheel shape is emerging, with spiral arms where star formation is concentrated. These galaxies are still actively forming stars, but at slightly more moderate rates than their younger counterparts. They're beginning to look like modern spiral galaxies, though they're still smaller and contain fewer heavy elements. At 5 billion light-years, 8.8 billion years after the Big Bang, we see galaxies that look quite similar to the modern Milky Way. They have well-defined spiral arms, central bulges, and structured disks. Star formation is ongoing but more measured. These galaxies have processed much of their gas through multiple generations of stars, enriching themselves with heavy elements. Planets are forming around these stars, and some of those planets might be developing the conditions necessary for life. At 2.5 billion light-years, 11.3 billion years after the Big Bang, we see mature spiral galaxies at their peak. Star formation continues, but many of these galaxies are approaching a steady state where star formation is balanced by stellar death. They've accumulated significant populations of older stars in their central bulges and halos. These are galaxies in their prime, much like the Milky Way today. And finally, at our present epoch, 13.8 billion years after the Big Bang, we see the modern population of spiral galaxies. Some are still actively forming stars. Others, in dense cluster environments, have had their gas stripped away and are becoming red and dead galaxies, where star formation has ceased. The diversity of galaxies at this epoch reflects the many different evolutionary paths galaxies can take. But here's what's truly fascinating about watching this evolution. We can also look forward in time, using computer simulations based on our understanding of physics, gravity, and star formation. And when we do, we see something unsettling. The future of the universe is not bright literally. Here's what will happen to a typical spiral galaxy like the Milky Way over the next trillions of years. In the near term, the next few billion years, galaxies will continue much as they are. Star formation will gradually decline as galaxies consume their gas reserves. The Milky Way and Andromeda will collide and merge, creating a new elliptical galaxy. Other galaxies in our local group will also eventually merge. But then, around 100 billion years from now, something dramatic happens. New star formation will cease entirely. The universe will have expanded to the point where no new gas can fall into galaxies. All the available gas will have been converted into stars or locked up in stellar remnants. The universe will contain only the stars that already exist and whatever can be recycled from dying stars. The universe will begin to dim. From 100 billion to 1 trillion years from now, the universe will be dominated by low-mass red dwarf stars, the slowest burning stars, which can live for trillions of years. One by one, the more massive stars will die, leaving behind white dwarfs, neutron stars, and black holes. The galaxies, or rather, the merged supergalaxies that remain from all the galaxy mergers, will be filled with dim red stars and the cooling remnants of dead stars. At 1 trillion years, the last of the bright stars will die. The universe will be dark, except for the faint glow of red dwarfs and the occasional white dwarf, warmed by gravitational contraction. The night sky, from any planet still remaining, will be completely black. The cosmic microwave background will have cooled to nearly absolute zero, providing no light or heat. Galaxies beyond one's own local merged supergalaxy will have moved beyond the cosmic horizon, carried away by cosmic expansion until they're unreachable and invisible. From 1 trillion to 100 trillion years, even the red dwarfs will die. They'll cool and become black dwarfs, gold, dark stellar remnants. The universe will enter the degenerate era where most normal matter exists as cold, dark stellar corpses. And then it gets even stranger. From 100 trillion years onward, galaxies themselves will begin to disintegrate. Stars will be flung out of galaxies through gravitational interactions with other stars. Over incomprehensible timescales, most stars will be ejected into intergalactic space, leaving behind only the central supermassive black holes surrounded by small, dense clusters of stellar remnants. Eventually, around 10,100 years from now, that's a 1 followed by 100 zeros, even protons, might decay, though this is theoretical. If they do, all normal matter will eventually dissolve into radiation and lighter particles. Stars, planets, everything made of atoms will gradually disintegrate. The final major structures to remain will be black holes, and these too will eventually evaporate through a process called Hawking radiation, discovered theoretically by Stephen Hawking in 1974. Black holes emit tiny amounts of radiation and slowly lose mass over incomprehensible timescales. A black hole with the mass of the Sun would take about 1,067 years to evaporate. Supermassive black holes, like the one at the center of M87, would take perhaps 10,100 years to evaporate completely. And then, in the unimaginably distant future, the universe will reach its final state, a cold, dark, nearly empty void, filled only with ultra-diluted radiation and perhaps some fundamental particles. all spreading farther and farther apart as space continues expanding forever. This is called the heat death of the universe, and according to our current understanding of physics, it's the ultimate fate awaiting everything we've seen on our journey. Every galaxy we visited, every star in those galaxies, every planet, every structure, all of it is temporary. All of it will eventually fade, decay, and disappear, leaving behind only darkness and void. This is called entropy, the tendency of all systems to move from order to disorder, from structure to uniformity. The universe started in an extremely ordered state, the Big Bang, and it's been sliding toward disorder ever since. Galaxies, stars, planets, life, these are all temporary eddies in the cosmic stream, brief moments of increased order in a universe moving inexorably toward maximum entropy and heat death. Now, this might sound depressing, but I want you to consider it from a different angle. Yes, everything is temporary. Yes, the universe will eventually become cold and dark. But that makes the now this cosmic moment when galaxies blaze with the light of trillions of stars, when planets orbit those stars, when life has emerged on at least one of those planets infinitely precious. We exist in a special time in cosmic history. We live in the stelliferous era, the age of stars, when the universe is filled with light and structure and possibilities. This era will last for trillions of years, but it's still finite. It's a brief, bright moment in an eternal cosmic timeline that begins with the Big Bang and ends in heat death. And we're here to witness it. More than that, we're here to understand it. We've gone from being creatures that crawled out of the African savanna to beings that can fly through every galaxy in the universe, at least in imagination, understand the past and future of cosmic structure, and contemplate our place in it all. Astronomer Brian Cox has said that we might be the only part of the universe that knows the universe is going to end. Think about that. The universe has created conscious beings, us, who can understand its own past, present, and future. We can look at the stars and know they will eventually die. We can look at galaxies and know they will eventually merge and fade. We can look at the universe itself and understand its ultimate fate. That's not sad, that's miraculous. It's also terrifying, beautiful, and profound all at once. But here's something that will shift your perspective again. While all of this is true, according to our current understanding, our understanding has been wrong before and will be wrong again. 100 years ago, we didn't even know other galaxies existed. 50 years ago, we didn't know the universe's expansion was accelerating. 20 years ago, we had no idea what dark energy was. Who knows what we'll discover in the next 100 years that might completely change our understanding of the universe's fate. Maybe there's a way to prevent heat death. Maybe the universe is cyclic and will eventually begin a new Big Bang. Maybe the multiverse is real and new. Universes are constantly being created. Maybe consciousness itself plays a role in physics that we don't yet understand. Maybe life will find a way to persist, adapt, and survive in ways we can't currently imagine. Or maybe the current picture is correct, and the universe really will end in heat death. Either way, we're lucky enough to be here now, in the stelliferous era, in the age of galaxies, when the universe is at its most complex, its most beautiful, its most alive. Here's your next retention oak. In the next section, we're going to explore the most mysterious components of galaxies, the things we can't see, but know must be there. We're going to dive into dark matter and dark energy, the invisible forces that control the fate of every galaxy we visited. And what we discover might suggest that the galaxies we can see are just the tip of a much stranger cosmic iceberg. But right now, think about this. The light from distant galaxies that enters your eyes has been traveling through space for billions of years. It's crossed incomprehensible distances, survived the expansion of the universe, avoided being absorbed by dust or gas, all to finally be captured by your eye at this exact moment. That light is connecting you directly to places and times unimaginably distant. You're not just looking at the universe, You're receiving messages from across space and time, messages encoded in photons that have been traveling since before Earth existed. You're part of a cosmic conversation that spans billions of years. And that's something no amount of entropy can ever take away. As we flew through every galaxy in the observable universe, we saw stars, gas, dust, and structure. But here's something mind-blowing. Everything we saw, all of it, represents only about 5% of the actual matter and energy in the universe. The other 95% is invisible, detectable only through its gravitational effects. This invisible majority consists of two mysterious components: dark matter, about 27% of the universe, and dark energy, about 68% of the universe. Let me tell you how we know these things exist, because it's one of the most fascinating detective stories in all of science. Dark matter was first hypothesized in 1933 by Fritz Zwicky, a brilliant and famously irascible Swiss astronomer working at Caltech. Zwicky was studying the Coma cluster of galaxies, one of the clusters we flew through earlier, and he noticed something strange. He calculated how fast the galaxies were moving within the cluster, and those speeds were way too high. According to his calculations, the galaxies were moving so fast that the cluster should fly apart. The visible matter in the cluster couldn't provide enough gravitational pull to hold it together. Zwicky proposed that there must be some kind of invisible dunkel materie, dark matter, providing the extra gravity. But his idea was largely ignored for decades. Zwicky had a reputation for being difficult to work with, and his dark matter hypothesis seemed too radical. Then in the 1970s, astronomer Vera Rubin made observations that forced the scientific community to take dark matter seriously. Rubin was studying the rotation curves of spiral galaxies, measuring how fast stars orbit at different distances from the galactic center. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just like the outer planets in our solar system orbit more slowly than the inner planets. But that's not what Rubin found. Instead, she discovered that stars at the edges of galaxies were orbiting just as fast as stars closer to the center. This flat rotation curve defied the predictions based on the visible matter in the galaxies. The only way to explain it was if each galaxy was embedded in a massive halo of invisible matter, extending far beyond the visible disk, a halo containing several times more mass than all the visible stars and gas combined. This was confirmed through multiple independent methods. Gravitational lensing, the bending of light by gravity, showed that galaxy clusters contain far more mass than we can see. Observations of colliding galaxy clusters, like the famous Bullock cluster, showed that the visible matter and the gravitational mass separate during collisions, with the dark matter passing right through, while the normal matter interacts and slows down. Computer simulations of galaxy formation showed that you couldn't create the observed large-scale structure of the universe without including massive amounts of dark matter to provide gravitational scaffolding for normal matter to collapse onto. The evidence is now overwhelming. Dark matter exists, and it outweighs visible matter by about 5 to 1. But here's the unsettling part: we still don't know what it is. It can't be normal matter made of protons and neutrons. We've ruled that out through measurements of Big Bang nucleosynthesis, process that created the first atomic nuclei in the early universe. It can't be black holes or other dark objects made of normal matter, because we would detect those through the gravitational effects. It must be something fundamentally different, particles that don't interact with light or normal matter except through gravity. The leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles, or axions. But despite decades of experiments looking for these particles, we haven't detected them yet. There are massive detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with normal matter. So far, nothing. This means that when we flew through every galaxy in the universe, we were actually flying through vast, invisible halos of something we don't understand, mysterious particles that have never been directly detected, but that completely dominate the gravitational dynamics of the cosmos. Think about that for a moment. The galaxies we can see, all those beautiful spirals and ellipticals, all those billions of stars, are just the visible tips of much larger structures. If we could see dark matter, galaxies would look completely different. Each visible galaxy would be surrounded by a massive, roughly spherical halo of dark matter extending far beyond the visible edge of the galaxy. These halos would be smooth and featureless, without the complex structures we see in normal matter. In fact, the visible parts of galaxies formed because dark matter halos existed first. In the early universe, dark matter began clumping under its own gravity before normal matter could. These dark matter clumps created gravitational wells, and normal matter fell into these wells, compressed, heated up, and eventually formed stars and galaxies. The visible universe we see is literally built on a dark matter foundation we can't see. But dark matter, as mysterious as it is, isn't even the strangest component of the universe. That distinction belongs to dark energy. Dark energy was discovered in 1998 by two independent teams of astronomers led by Saul Perlmutter, Brian Schmidt, and Adam Rees, who won the Nobel Prize for this discovery in 2011. They were studying Type Ia supernova stellar explosions that have a consistent brightness, making them useful as standard candles for measuring cosmic distances. What these teams discovered shocked the physics community. The expansion of the universe is not slowing down, as everyone expected. It's speeding up. Galaxies aren't just moving away from each other, they're accelerating away from each other. Something is pushing the universe to expand faster and faster, working against gravity's attractive pull. This something was dubbed dark energy, and it's the most mysterious thing in all of physics. We don't know what it is. We don't know where it comes from. We don't even know if it's really a form of energy, or if it's something else entirely, maybe a property of space-time itself, or a sign that Einstein's theory of gravity breaks down on cosmic scales. The simplest explanation is that dark energy is Einstein's cosmological constant, a constant energy density filling all of space. Einstein actually proposed this idea in 1917 to keep the universe static before we knew the universe was expanding, then later called it his biggest blunder when Hubble discovered cosmic expansion. But it turns out Einstein might have been right after all, just for the wrong reasons. The cosmological constant would cause the universe to expand exponentially, exactly what we observe. But here's the problem. When physicists try to calculate what the value of the cosmological constant should be based on quantum field theory, they get an answer that's wrong by a factor of 10,120. That's not a typo. The theoretical prediction is off by 120 orders of magnitude. It's been called the worst theoretical prediction in the history of physics. So we're left with this, the dominant component of the universe, making up 68% of everything, is something we don't understand at all. It's causing the universe to expand faster and faster, and we have no idea why or what it really is. Here's why this matters for our journey through galaxies. Dark energy determines the ultimate fate of the universe. If dark energy remains constant, the universe will expand forever, leading to the heat death scenario I described earlier. If dark energy gets stronger over time, a hypothesis called phantom energy, the universe could end in a big rip, where the accelerating expansion eventually tears apart galaxies, solar systems, planets, and eventually atoms themselves. If dark energy weakens over time, the expansion could slow down or even reverse, leading to a big crunch where the universe collapses back in on itself. We're living in a universe where 95% of the content is mysterious, where the visible galaxies we explored are just a small fraction of what's really out there, and where the future is determined by forces we don't understand. And yet, despite this profound ignorance, we've managed to learn an extraordinary amount. We've mapped the distribution of dark matter using gravitational lensing. We've measured the properties of dark energy using supernova and the cosmic microwave background. We've created detailed computer simulations showing how dark matter and dark energy work together to create the cosmic web of galaxies we observe. This is one of the most impressive achievements of human intelligence. We've deduced the existence and properties of things we can't see, using only their indirect effects and the laws of physics. It's like a detective solving a mystery where the criminal is invisible but leaves footprints everywhere. Let me paint you a complete picture of what a galaxy really is, including the invisible components. At the center, there's a supermassive black hole, millions to billions of times the mass of the Sun. Surrounding it is a dense bulge of old stars. Extending outward in spiral galaxies are spiral arms containing younger stars, gas, and dust. This is where star formation happens. The visible disk of the galaxy extends for tens to hundreds of thousands of light years. But that's only the beginning. Surrounding the entire visible galaxy is a spherical halo of old stars and globular dense clusters of ancient stars that formed in the early universe. This stellar halo extends well beyond the visible disk. And surrounding everything is the dark matter halo, a roughly spherical distribution of invisible matter extending for hundreds of thousands of light years, containing several times more mass than all the visible components combined. This dark matter halo is the dominant gravitational structure, the foundation upon which everything else is built. When galaxies collide and merge, their dark matter halos pass right through each other, while the visible components interact violently. When galaxies move through galaxy clusters, they can have their gas stripped away by interactions with the hot intergalactic medium, but they keep their dark matter halos. And pervading everything, the galaxies, the dark matter halos, the space between galaxies, everything is dark energy, causing all of this to accelerate apart. This is the complete picture of what we were really flying through. A universe where the visible galaxies are small islands in vast oceans of dark matter, all of it pushed apart by mysterious dark energy. We're like people looking at clouds and thinking we understand weather, not realizing that the clouds are just tiny visible features in a much larger, invisible atmospheric system. But here's what gives me hope in the face of all this mystery. Every time we've encountered something mysterious in the past, we've eventually figured it out. We didn't understand what stars were until we developed nuclear physics. We didn't understand what galaxies were until we developed powerful telescopes. We didn't understand how galaxies formed until we developed supercomputers capable of simulating cosmic evolution. The mystery of dark matter and dark energy is just the latest challenge. Somewhere right now, there might be a scientist doing an experiment or making an observation that will crack one of these mysteries. Maybe dark matter will be directly detected next year or next decade. Maybe a new theory will explain dark energy. Maybe the James Webb Space Telescope will find something completely unexpected that gives us a crucial clue. Or maybe the answer will come from someone watching this video. Maybe you're a student who will go on to study physics or astronomy. Maybe you'll be the one who finally figures out what dark matter is. Maybe you'll develop the theory that explains dark energy. The next generation of scientists is alive right now, and some of them might be watching these words. Science is a collective human endeavor spanning generations. The astronomers studying galaxies today are building on work done by Hubble, Rubin, Zwicky, and countless others. And the scientists of tomorrow will build on the work being done today. That continuity across time, that collaborative quest for understanding, is one of humanity's greatest achievements. Here's your next retention hook. In the next section, we're going to do something extraordinary. We're going to look at what we learned from our journey through every galaxy and use it to understand our own place in the universe. We're going to connect the cosmic scale we've explored to your personal life, your daily existence, and your sense of meaning and purpose. Because ultimately, this journey isn't just about galaxies, it's about you. But before we make that connection, take a moment to appreciate the sheer audacity of what we've done. We've journeyed through 2 trillion galaxies. We've explored 46.5 billion light years of space. We've crossed 13.8 billion years of time. We've confronted mystery on a scale that should be crushing 95% of the universe, is made of stuff we don't understand, and yet we've persisted in trying to understand it anyway. That persistence, that refusal to accept ignorance, that determination to understand, even when understanding seems impossible, that's the human spirit at its finest. And you're part of it, just by being curious enough to watch this video and think about these ideas. Now, let's bring it all home. We've completed our impossible journey through every galaxy in the observable universe. But the most important part remains. What does any of this mean for you, specifically, as an individual human being living on Earth in the 21st century? This isn't an abstract question. The cosmic knowledge we've gained should fundamentally change how you see yourself, your problems, your achievements, your relationships, and your place in existence. Let me show you how. First, let's talk about perspective. You've probably heard the phrase cosmic perspective before, but after flying through 2 trillion galaxies, you now truly have one. You've seen the incomprehensible scale of the universe firsthand. So let's start with the most obvious implication. Your problems, in cosmic terms, are incredibly small. That doesn't mean they're not real or important. They absolutely are, but it means they're not permanent, not insurmountable, and not the center of the universe. That argument with your friend, that deadline at work, that rejection you experienced, that anxiety keeping you up at night, these are real challenges for you, but they're not cosmic catastrophes. The universe has survived for 13.8 billion years. It's produced 2 trillion galaxies and more than a septillion stars. It will continue long after you, and everyone you know is gone. Now, some people find this depressing, the feeling of cosmic insignificance. But I want you to consider the opposite perspective. You're significant precisely because you're so improbable. Think about what had to happen for you to exist. The universe had to come into being 13.8 billion years ago in a Big Bang. Inflation had to occur to make the universe smooth and flat. Dark matter had to clump to create gravitational wells. Normal matter had to fall into those wells to create the first stars and galaxies. Those first stars had to explode as supernova to create heavy elements. Those heavy elements had to be incorporated into second-generation stars. One of those stars had to be our Sun, forming 4.6 billion years ago in a molecular cloud in one spiral arm of one galaxy among trillions. That star had to form a planetary system, with one planet Earth at just the right distance to have liquid water. That planet had to be large enough to hold an atmosphere, but not so large that it became a gas giant. It needed a large moon to stabilize its axial tilt. It needed a magnetic field to protect it from solar wind. It needed plate tectonics to regulate its climate over billions of years. Then life had to emerge from chemistry, a process we still don't fully understand. That life had to survive multiple mass extinctions, including asteroid impacts, volcanic eruptions, and climate changes. It had to evolve over billions of years, developing photosynthesis, multicellularity, sex, complex body plans, nervous systems, and eventually consciousness. One lineage of that life had to leave the ocean and colonize the land. That lineage had to survive the asteroid impact that killed the dinosaurs. It had to evolve into primates, then apes, then early hominids, then modern humans. Your specific ancestors, going back thousands of generations, had to survive diseases, famines, wars, and accidents. They had to meet the right partners at the right times. They had to have children, and those children had to survive and reproduce. And finally, your specific parents had to meet out of all the billions of humans on Earth. They had to have you, the result of one specific sperm meeting one specific egg out of millions of possibilities. If any of those millions of sperm had succeeded instead, a different person would exist, but not you. The probability of you existing is so astronomically low that it's essentially zero. And yet here you are. You are a cosmic accident, so improbable that it defies calculation, but you happened anyway. Every atom in your body has been on an incredible journey. The hydrogen atoms in your body, mostly in water, were created in the Big Bang. The carbon atoms were forged in the cores of massive stars. The oxygen you breathe was created when those stars exploded as supernova. The calcium in your bones, the iron in your blood, the copper and zinc and selenium, all of it was created in stellar furnaces and stellar explosions. These atoms have existed for billions of years. They've been part of nebulae, comets, asteroids, the early Earth, ancient oceans, dinosaurs, ancient plants, other humans. They've circulated through the biosphere for eons. And right now, for this brief moment in cosmic time, they're organized into a pattern called you. You are a temporary arrangement of ancient stardust that has become conscious, capable of thinking, feeling, wondering, and understanding. You're a way for the universe to know itself. As Carl Sagan said, you're a mechanism through which the cosmos reflects on its own existence. And that means your life has inherent cosmic significance, regardless of your achievements, your social status, or your influence. The simple fact that you exist, that you're conscious, that you can look up at the night sky and wonder, that's miraculous. You're participating in the most profound process in the universe, matter becoming aware of itself. But let's get even more personal. How should this cosmic journey change how you live your daily life? First, it should give you humility. You're one human among 8 billion on Earth, living on one planet among trillions of planets, in one galaxy, among 2 trillion galaxies in the observable universe. Your opinions, your beliefs, your certainties, they're not universal truths. They're the products of your specific circumstances, your culture, your experiences. A little humility about your own knowledge and perspective is appropriate given the vastness of what you don't know. Second, it should give you courage. If the universe can create 2 trillion galaxies from a point smaller than an atom, if it can turn hydrogen into stars, and stars into complex elements, and complex elements into life, and life into consciousness, then your problems are solvable. The same universe that accomplished all of that is working through you. You have within you the same creative force that built galaxies. Use it. Third, it should give you compassion. Everyone you meet is on the same cosmic journey you are, a brief flicker of consciousness in an incomprehensibly vast universe, trying to make sense of their existence, trying to find meaning and connection. Everyone is dealing with the same fundamental questions you are. That angry person who cut you off in traffic? They're stardust trying to figure out how to be. That annoying coworker? Stardust. That person you disagree with politically? Stardust. We're all in this together, all made of the same cosmic material, all conscious fragments of the universe experiencing itself. Fourth, it should give you urgency. Your time is limited. The atoms that currently make up your body will disperse after you die, becoming part of other things: soil, water, air, eventually other living things. The pattern that is you will dissolve. This isn't meant to be morbid, it's meant to be motivating. You have a finite time to experience existence, to learn, to love, to create, to contribute. Don't waste it on things that don't matter to you. Don't postpone the important things. Don't leave the critical words unsaid. The heat death of the universe won't come for trillions of years, but your personal heat death could come much sooner. Use your time. Fifth, it should give you wonder. You live in an age where you can know about 2 trillion galaxies, where you can see images of galaxies as they were billions of years ago, where you can understand the fundamental laws that govern reality. You live in the brief window of cosmic time when the universe is full of stars and structure and life. You live on a planet where evolution has produced millions of species, where mountains rise and oceans flow, where consciousness has emerged and built civilizations. You live in the most interesting time in human history, a time when we've developed the technology to destroy ourselves, but also the wisdom to potentially avoid doing so. When we're on the cusp of becoming a spacefaring species, when we're beginning to understand our place in the cosmos. You're alive during the transition from planetary civilization to potentially cosmic civilization. That's worth feeling wonder about, worth feeling grateful for. Now let me address something directly. Some of you watching this might be going through difficult times. Depression, anxiety, loneliness, grief, failure, pain. These are real and valid experiences that cosmic perspective doesn't magically erase. If you're struggling, please know that your pain matters, that you matter, and that help is available. Talk to someone. Reach out. You're part of this cosmic story, and your chapter isn't over yet. But I also want to suggest that cosmic perspective can provide a kind of relief. When you're depressed, your mind often tells you that your current suffering is permanent, that things will never get better, that you're fundamentally broken. Cosmic perspective reminds you that nothing is permanent. The universe changes constantly. Stars are born and die. Galaxies merge and evolve. The Earth's continents drift across the surface over millions of years. Species come and go. Civilizations rise and fall. You are also changing, constantly. The atoms in your body are replaced over time. Your cells die and are regenerated. Your brain rewires itself based on your experiences. Your thoughts and feelings are patterns of neural activity that shift moment by moment. The you of today is not the you of yesterday or tomorrow. If everything in the universe is temporary and constantly changing, then so is your suffering. It feels permanent, but it's not. It will change. You will change. New patterns will emerge. That doesn't mean change is easy or automatic. It often requires effort, support, and time. But change is possible because change is the fundamental nature of reality. Let me also address meaning. One of the most common existential questions is, what's the meaning of life? We've flown through 2 trillion galaxies, seen the birth and death of cosmic structure, confronted the ultimate fate of the universe. Does any of this give us an answer? Here's what I think. The universe doesn't come with pre-installed meaning. Galaxies don't have purpose. Stars don't have goals. Dark matter doesn't wonder why it exists. The cosmos simply is a vast, complex, evolving system following physical laws. But you're different. You have consciousness, which means you can create meaning. You can look at the universe and decide what matters to you. You can choose what to value, what to pursue, what to care about. You're not just a passive receiver of cosmic fate. You're an active participant in creating your own story within the larger cosmic story. The meaning of your life is whatever you decide it is. For some people, it's family and relationships. For others, it's creating art or music or literature. For some, it's scientific discovery or technological innovation. For others, it's alleviating suffering or fighting injustice. For many, it's some combination of multiple things. There's no cosmic authority that's going to tell you you chose wrong. You get to decide. That's both liberating and terrifying. You have freedom, but also responsibility. My personal suggestion, having taken you through this journey, make your life about connection and growth. Connect with other people, with nature, with ideas, with art, with the cosmos itself. And grow in knowledge, in compassion, in capability, in wisdom. Because connection and growth are what made this cosmic journey meaningful. We connected abstract knowledge about galaxies to personal significance. We grew in our understanding across every section. Connection and growth seem to be fundamental patterns in the universe. Atoms connect to form molecules. Molecules connect to form cells. Cells connect to form organisms. Organisms connect to form ecosystems. People connect to form societies. Societies connect to form civilizations. Maybe meaning emerges from that same pattern of connection at every scale. And growth is everywhere in the cosmos. The universe grew from a point to 93 billion light-years across. Galaxies grew from small protogalaxies to massive structures. Stars grew from clouds of gas. Planets grew from disks of dust. Life grew from simple chemistry to complex ecosystems. Consciousness grew from simple awareness to self-reflection and understanding. You're part of that cosmic pattern of connection and growth. When you learn something new, you're participating in the universe's growth in self-understanding. When you connect with another person, you're participating in the universe's pattern of increasing complexity in organization. You're not separate from the cosmos, you're a part of it, an expression of it, a way it experiences itself. Here's your final retention hook before we reach our conclusion. In the last section, we're going to zoom all the way back from the cosmic scale to your location right now and answer the question we started with. Are we flying through galaxies, or are they flying through us? The answer is going to reframe everything we've discussed. But right now, I want you to do something. Pause this video for a moment. Look around you at your physical surroundings. Notice the objects near you, the device you're watching this on, your own body. Everything you're seeing is made of atoms that were once inside stars in distant galaxies. Everything around you is made of the same fundamental particles that fill the cosmos. You're not in the universe, you are the universe, locally concentrated. Every breath you take exchanges molecules with the atmosphere that's been around for billions of years. Every thought you think is a pattern of electrical and chemical activity happening in the most complex structure we know of in the entire universe, your brain. Feel your connection to everything we've discussed. You're not a tourist observing the cosmos from outside. You're an integral part of it, and that changes everything. Now let's bring our journey to its final conclusion. We're decelerating now, flying back across the cosmos toward Earth at impossible speed. The distant galaxies blur past us first billions per second, then millions, then thousands. We're retracing our path through the observable universe, heading home. As we slow down, passing through the local galaxy clusters, through the Virgo supercluster, through our local group, and finally approaching the Milky Way, I want you to notice something. We're not flying through static space. Everything is moving. The Milky Way is rotating, taking our solar system on a 225 million year orbit around the galactic center. But the Milky Way itself is also moving, falling toward the Andromeda Galaxy at 250,000 miles per hour. And both galaxies are moving together with the rest of the local group toward the Virgo cluster. And the Virgo supercluster is moving towards something called the Great Attractor, a massive concentration of galaxies 150 million light-years away. And all of this is moving relative to the cosmic microwave background. When you add up all these motions, Earth is moving through space at about 1.3 million miles per hour, the speed I mentioned at the very beginning of this video. You're on a planet orbiting a star, in a galaxy moving through space, in a universe expanding and accelerating. You've never been still. You've always been flying through the cosmos. We're approaching Earth now, our home planet coming back into view. From space, it looks like the famous pale blue dot photograph taken by Voyager 1 in 1990. Carl Sagan's words about that image are worth remembering. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam, every galaxy we visited, every star, every planet, it all provides context for understanding how special and fragile this little world is. Earth is the only place in the entire observable universe where we know life exists. It might be one of countless inhabited worlds, or it might be unique. We don't know yet. But we do know it's rare. We've never found another place like it. We're descending through the atmosphere now, that thin layer of air that makes life possible. From space, the atmosphere looks impossibly thin, like the skin on an apple. All of life on Earth, all of human history, everything we've ever done or will do, happens in this thin shell of gas surrounding a rocky ball in space. And now we're back where we started your location, wherever you're on Earth. But you're not the same person who started this journey. You've been changed by what you've seen. You've experienced something impossible. You've touched the edge of existence. Now let me answer the question I posed at the beginning. Are we flying through galaxies, or are they flying through us? The answer is both, and neither. Here's the truth. The distinction between you and the universe is artificial. It's a convenient fiction we maintain, because our everyday experience suggests we're separate entities. You're you, and everything else is out there. But that separation is an illusion. The atoms in your body came from galaxies. They were forged in stellar cores, dispersed by supernova explosions, collected into new stars and planets, and eventually organized into the pattern called you. You're not separate from the galaxies. You're made of them. You're a local concentration of galactic material that has become conscious. When you breathe, you exchange atoms with the atmosphere. Some of the oxygen molecules you just inhaled were breathed by other people, by plants, by animals throughout Earth's history. You're constantly exchanging matter with your environment. The boundary between you and not you is permeable and arbitrary. Your body completely replaces most of its atoms over the course of years. The you of 7 years ago was made of mostly different atoms than the you of today. So are you the atoms or the pattern? You're the pattern and information pattern maintained in physical substrate that's constantly being replaced. And where did that pattern come from? It came from your parents' DNA, which came from their parents, going back through billions of years of evolution, back to the first self-replicating molecules, back to the chemistry of the early Earth, back to the stellar nucleosynthesis that created the elements, back to the Big Bang that created the fundamental particles. You're not a thing, you're a process. You're a verb, not a noun. You're an ongoing pattern of organization and energy flow that's been continuous since the beginning of the universe. The atoms may change, but the pattern, the information persists and evolves. So when we ask, are we flying through galaxies, or are they flying through us, we're asking the wrong question. It assumes a separation that doesn't really exist. We are the galaxies, locally concentrated and temporarily organized into conscious patterns. The galaxies are us, dispersed across cosmic space and time. When you look up at the night sky and see the Milky Way, you're not looking at something separate from yourself. You're looking at your extended body, the larger system you're part of. Those stars are your distant cousins, made of the same fundamental particles, following the same physical laws, part of the same cosmic story. Thich Nhat Hanh, the Vietnamese Buddhist monk and peace activist, taught about interbeing, the idea that nothing exists independently, that everything is with everything else. A cloud is with a river, which is with the ocean, which is with the rain. You can't point to where the cloud ends and the river begins. They're all part of one continuous process. You are with the galaxies. You can't draw a clear line between where the universe ends and where you begin, because there is no such line. You're a wave in the cosmic ocean, temporarily distinct but never separate. This isn't just poetry or philosophy, it's physics. Quantum mechanics tells us that particles don't have definite positions until they're measured. They exist in superpositions of multiple states. The universe at the quantum level is deeply interconnected through entanglement particles that have interacted, can remain correlated, even when separated by vast distances. General relativity tells us that space-time itself is flexible and dynamic, curved by matter and energy. You're not in space-time, you're made of space-time. Your mass curves the fabric of space around you. You're a wrinkle in the cosmic fabric. Cosmology tells us that everything in the observable universe was once compressed into a space smaller than an atom. Everything was connected. Everything was part of the same system. Expansion has separated things spatially, but the fundamental connection remains. Every particle in your body was once in contact with every other particle in the observable universe. So what does this mean practically? It means when you help another person, you're helping the universe help itself. When you damage the environment, you're damaging yourself. When you create beauty, you're participating in the universe's creative process. When you learn and grow, you're expanding the universe's self-awareness. It also means you're never truly alone. Loneliness is the feeling of separation, but that separation is an illusion. You're always connected to everything, to the air you breathe, to the ground beneath your feet, to the food you eat, to the people around you, to the planet, to the solar system, to the galaxy, to the entire cosmos. You're an integral part of an incomprehensibly vast and beautiful system. Alan Watts, the philosopher and interpreter of Eastern thought, sighed, "You are an aperture through which the universe is looking at and exploring itself. That's what you are, a window through which the cosmos experiences itself, learns about itself, creates and discovers and wonders." And here's the most beautiful part. Every other conscious being is another such aperture. When you connect with another person, really connect, with empathy and understanding, two parts of the universe are recognizing themselves in each other. You're looking at another version of yourself, another expression of the same cosmic process that created you. The ancient Hindu greeting Namaste means the divine in me recognizes the divine in you, or the universe in me recognizes the universe in you. After our journey through every galaxy in the observable universe, you can now understand that literally, the atoms and energy and pattern that create you are the same as the atoms and energy and patterns that create everyone and everything else. We're all temporary expressions of the same underlying cosmic reality. This is why love and compassion are not just nice ideas, they're recognition of truth. When you feel love for another person, you're feeling the universe's love for itself. When you feel compassion for suffering, you're feeling the universe's awareness of its own pain. When you feel joy, you're feeling the universe celebrating its own existence. You're not a separate entity trying to survive in a hostile universe. You're the universe itself, experiencing what it's like to be human at this time, in this place. So what should you do with this knowledge? First, remember it. Don't let the ordinary demands of daily life make you forget the cosmic perspective you've gained. Regularly remind yourself that you're a conscious part of the universe, experiencing itself. Second, share it. Talk about these ideas with others. Show people images of galaxies. Explain what you've learned. Help others gain cosmic perspective. The more people who understand their connection to the cosmos, the better humanity will be at making wise decisions about our collective future. Third, act from it. Let your cosmic perspective inform your choices. Be kind to others, they're you in a different form. Protect the environment, it's literally your extended body. Pursue knowledge and growth. That's the universe expanding its self-understanding through you. Create beauty. That's the universe expressing its creativity. Fight against injustice. That's the universe working toward greater harmony. Fourth, appreciate it. Take time regularly to feel awe and wonder at your existence and at the universe you're part of. Look up at the stars. Watch the sunset. Observe the complexity of a flower or a tree or an insect. Feel grateful for the impossible improbability that you exist at all. And finally, be patient with yourself and others. We're all cosmic infants, barely beginning to understand what we are and where we are. Humanity has only known that other galaxies exist for about 100 years. We've only had scientific understanding of our place in the cosmos for a few generations. We're still learning how to be conscious matter, how to be the universe aware of itself. Mistakes will be made. Suffering will occur. But the general trajectory, over enough time, seems to be toward greater complexity, greater consciousness, greater understanding. The universe spent 13.8 billion years getting to the point where it could understand itself. You're part of that ongoing process. Our journey through every galaxy in the observable universe is complete, but your personal journey through the cosmos continues. Every day you live is another chapter in the universe's autobiography. Every choice you make shapes not just your life, but the evolution of consciousness itself. You started this video as a person watching a YouTube video. I hope you end it as something more, as a conscious, integral part of the cosmos, aware of your connection to everything, ready to live your life with cosmic perspective and purpose. The 2 trillion galaxies we visited are not distant, separate objects. They're your home, your extended body, your family. You're flying through them, and they're flying through you, and ultimately, there's no meaningful distinction between the two. You're all part of the same cosmic story, the same universal dance of matter and energy, and information evolving and exploring and experiencing. And that story is still being written. Your chapter is not complete. What will you do with your brief time as a conscious arrangement of stardust? How will you participate in the universe's ongoing adventure of self-discovery? The cosmos has spent 13.8 billion years creating you. It's forged elements and stellar cores, shaped galaxies through gravity, evolved life through natural selection, and developed consciousness through billions of years of neural evolution, all to produce the person reading these words right now. You are the universe's gift to itself, a way for existence to experience and understand itself. That's not just significant, that's miraculous. Thank you for taking this journey with me. Thank you for being curious enough, patient enough, and open-minded enough to spend hours contemplating galaxies and your place among them. Thank you for being another conscious node in the universal network, another aperture through which the cosmos knows itself. Before you go, one final request. Share this video with someone who needs cosmic perspective. Someone who's struggling, someone who's curious, someone who's forgotten how amazing existence is. Help spread the understanding that we're all connected, that we're all part of something vastly larger than ourselves, that we're all made of stars. And remember, you're not in the universe. You are the universe. Every atom of your being is a universe unto itself, and you contain multitudes. You're simultaneously infinitely small and cosmically significant. You're a temporary pattern with eternal connections. The journey through every galaxy in the observable universe isn't just a thought experiment. It's a metaphor for the journey of consciousness itself, expanding from limited awareness to cosmic understanding, from feeling separate to recognizing unity, from seeing galaxies as distant objects to understanding them as parts of yourself. Now go forth with this knowledge. Look up at the night sky differently. Treat yourself and others differently. Live differently, knowing what you know about your true nature and your cosmic context. The universe is vast, but you're not lost in it. You're at home in it, because you are it. And that makes all the difference. Safe travels, fellow stardust. Until we meet again among the stars.